Hello, everyone. This is Reza Shokri from NUS, and I would like to thank the organizers for having me for this research talk. I'm very excited about sharing the results of the research we have been working on for quite some time on a very important problem of quantifying the privacy risks in machine learning models, and more specifically, modeling the dynamics of differential privacy in such algorithms. So this is the joint work with two of my PhD students, Rishav and Jie-Yuan, who has been leading this effort. So when we talk about privacy in machine learning and the risks of machine learning on data privacy, there are two different ways that privacy risk could be measured. One is with respect to direct leakage, when an entity who is running the training algorithm or is running the inference has direct access to the training data or the user's queries. So it's very obvious that in these cases, if that entity is not trusted, data privacy is violated. And using secure multi-party computations, trusted hardware, and similar techniques would enable us to do the computation without revealing information about the data during the time of computation. So the more subtle type of information leakage is the indirect leakage through the results of the computation. The previous defense techniques cannot prevent this because the output of the computation, which is the model parameters or the predictions produced by the model, would leak information about the data on which the model is trained. And here, by leakage, basically we mean the information that an adversary can infer about members of the training set, which he could not infer about the underlying data, which is different. So if there's some specific information that applies to members of the training data, which it cannot infer by having access to the underlying distribution, then it's the fault of the training algorithm that has leaked this information out to the adversary. And to be more precise, one can design an indistinguishability game where the adversary is asked to distinguish between two models which are trained on two neighboring data sets, which they differ in one record. So for example, the adversary can see the predictions from these models or observe the model parameters. And if he fails, it means that these two algorithms are indistinguishable from each other. And then privacy with respect to the training data is preserved. If the adversary wins this game, it means that the algorithm leaks information about the specific data point in the training set and violates their privacy. There are specific attacks called membership inference attacks that try to exploit this type of information leakage. Given the predictions of a model on a data point, or the predictions or the model parameters, the objective of the attacker is to find information in the observables that can enable him to distinguish between the two cases where the data was part of the training set or not. So this has been shown to be very powerful attacks and could be used as a way to quantify information leakage through models. And this is what we have actually implemented and is available as an open source tool, which we call machine learning privacy meter. For any algorithm, machine learning algorithm, and a data set, it would measure how much is the power of membership inference attacks on those models. So this helps you to distinguish which algorithm performs better or which data points in the training set are at a higher risk. But going back to the indirect leakage and specifically the information leakage of models through their parameters. We ask, okay, so how can we mitigate this risk? How can we design a training algorithm that can provably prevent inference attacks to have an arbitrary high power for a given error? So to prevent that, differential privacy mechanisms are designed. Basically, the definition of differential privacy is to bound the distinguishability between the two algorithms. So if you have a randomized algorithm and we have these two parallel worlds where the same algorithm runs on two data sets that differ in one record, we want, according to the definition of differential privacy, that the outputs of these algorithms on all possible events be indistinguishable from each other up to a certain multiplicative distance factor e to the power of epsilon with the probability close to 1 minus delta. So this is one way to define differential privacy, and it's a notion of distance between two probability distributions. Another way to define it is to compute the Renyi divergence between two probability distributions at an order alpha, and prove the bound on this divergence between the two distributions. And this could be converted back to the epsilon delta differential privacy for any delta. So basically, when alpha is infinite, this is equivalent to epsilon dp. And also, it's very easy to compose differential privacy algorithms using their RDP bound. For a given alpha, you can just add their epsilon. So this is the notion of distance that we are going to use in this talk for our analysis. The algorithm that I want to analyze is this iterative gradient descent or stochastic gradient descent algorithms. For training a model, you have a training set D of size n, and what you do is that you construct some mini batches by either partitioning the training set into n over b partitions, or sampling b data points from the data set with replacement. So here's something which is important to note here is that in this talk, I refer to one iteration as operating on n over b mini batches. All right. Then for each mini batch, we run the gradient descent algorithm by computing the average gradient of the model given its current parameter with respect to the data in the on the data in the mini batch, and randomizing that gradient to satisfy differential privacy, and moving in the opposite direction of that gradient on the model parameter space, so to have the parameters for the next update. Then we just continue this on next mini batch and move on. After we are done with one iteration, then we just move to the next iteration. So the question is, how much is the privacy loss of this algorithm? One easy way to quantify the total privacy loss of this algorithm, if you go over multiple iterations, multiple epochs, is to just compose the privacy loss of each parameter update. So Here, if you have randomly sampled the data for the mini batches, the privacy loss for each mini batch is 2 alpha L square over sigma square, assuming that the loss function is L Lipschitz. And we have N over B times K updates when K passes over the data. And the epsilon would just be the addition of all the leakage in one updates throughout the training. So this is a baseline for composition. But can we do better? It depends on how we sample the data for the mini batch. So let's consider the case that we are sampling the data for each mini batch with replacement from the original training data set. And now the question that we ask is that how much is the indistinguishability between running the training algorithm on a data set D and a data set D prime, which is different in one record, right? So there is one data point, which is, let's say, in one of them and is not in the other one. And that data point, with a small probability, B over N, could be in any of the mini batches, right? So we can use this uncertainty of the probability that the differing data point is in a mini batch to amplify the privacy bound that we have computed to reduce the privacy bound over this algorithm. And this is what is known as the privacy amplification by subsampling. It gives us an N square over B square amplification. So when we multiply it by the number of updates in the whole algorithm and multiply it by the leakage for one update, we get this line, which is much better than the baseline. Again, this is a composition-based algorithm that just composes these algorithms, but incorporating this uncertainty that differing data point could be in any mini batch. If you change the setting a little bit, first of all, assuming that the data that we get from the training set is partitioned into N over B mini batches. So there is no overlap between the data in different mini batches. And secondly, assume that the information about the model parameters after each update is not observable, right? So after we compute the parameters for and update the parameters for after each mini batch, we just pass it to the next one, and at the end of one iteration, when we go over the whole training set, then that's where we want to quantify the privacy loss. And then we use composition across different iterations. So something which is very important here in the analysis of this way of distributing data in different mini batches is that the differing data points between dataset D and D prime will appear in one single mini batch. And the computations on the other mini batches do not leak information about this one, but the randomization that we do in that can help us to tighten the bound on the information leakage about the training data. And this is what we see here, that the blue curve shows that, so without loss of generality, assume that that differing data point is in the first mini batch. So at the beginning of one iteration, when we observe a data point, if you update on one mini batch where the differing data point is there, then there's a jump in privacy loss because we are leaking information about that data point. But over time, that information the bound on the privacy loss exponentially goes down due to the randomness of subsequent parameter updates in the same iteration. But at the end of the iteration, we land on where we were in the privacy by subsampling, privacy amplification by subsampling analysis. The settings are different, but the privacy values would remain the same at the end of each iteration. Throughout an iteration, then we have a different analysis, but from one iteration to the other one, the privacy loss matches. And one thing which is also important is that in this case, if you assume that actually the adversary will just observe the parameters at the end of an iteration, then the baseline also shifts. Then also the baseline in one iteration will leak as much as one update. So the baseline also gets a bit shifted, gets a bit tighter than the case where we have subsampling. So this is all great compared to the baselines, compared to simple way of composing. We are taking advantage of this extra uncertainty due to the hiding the intermediate steps or due to the subsampling to tighten our privacy bound. But let's look at the results. One observation is that this analysis accounts for the privacy loss over all iterations, in the sense that it would see, because these are all composition-based techniques, it's true that within one iteration, the privacy analysis is different, but we just add up the privacy loss for multiple iterations. And even if the state of the algorithm is private, throughout the training, up to iteration K, you're still accounting for the privacy loss at the intermediate iterations. So that is basically equivalent to assuming that the adversary observes the model parameters at the end of each iteration, which is a very strong threat model, an unnecessarily strong threat model. So this was basically the motivation for designing privacy amplification by iteration, but that analysis applies to the updates within one iteration. Another observation is that as we see, the privacy loss increases with a linear rate from one iteration to the other one. So if you look at the contribution of iteration number 1 in the training process and the contribution of iteration number K on the total privacy loss, they are the same. The first time that I observed the whole data, the last time that I observed the whole data, they contribute equally to the total privacy loss. Which doesn't seem to be necessary. And actually, according to the results that we have on various sampling based techniques and also randomized gradient based algorithms, that they show that these algorithms converge in distribution to their stationary distribution after many iterations. We should get a different bound for privacy. So intuitively, if the model is converging in distribution, the influence of the training data on the model parameters decreases over time. Initially, they can change the distribution significantly, and that is what should be considered in the computation of the privacy loss. But after the model has convergent distribution, effectively doing another iteration would not change that distribution significantly. So the privacy loss should converge. That's the hypothesis that we have. So to try to prove that hypothesis and quantify the privacy loss throughout the training process, we are interested in quantifying the differential privacy dynamics of this stochastic process. We have an algorithm that looks at the training data, updates the parameters. So the distribution over the model parameters changes. Assume that the state of the algorithm remains private. And only at the end of iteration K, we are sampling from that distribution, and we are sending and releasing that as the model parameters. What we are interested in is how does privacy loss changes over time. So if you're releasing the model at iteration K, we are interested in measuring how much the privacy loss at iteration K changes with respect to the privacy loss at iteration K minus 1. And we want to quantify this using Renyi divergence. So let's focus on a particular algorithm. So we choose noisy gradient descent, but the results could be applied to the other similar algorithms. In the noisy gradient descent algorithm, so what we do is that over K iterations, in each iteration, we just compute the total gradient on the whole data set. And similar as the algorithm, similar to the algorithm that I discussed before, we compute the average gradient, you add noise, and update the model parameters. So this simplifies the analysis because then all these different ways to sample the mini batches, data for the mini batches, is abstracted away because I'm just looking at the whole data in each update. And I want to know how the privacy loss over different iterations changes. Again, the assumption is that the state of the algorithm should remain private. If you use composition algorithms, the prior work that we just discussed, then of course for different values of alpha, as we said, there's this linear rate for increase in epsilon, where epsilon for the particular algorithm that we just saw last slide, the epsilon is alpha. S here is the sensitivity of the total gradient. Over 4n square, n is the size of the data set, sigma square, where sigma is the random, the variance, sigma square is the variance for the Gaussian noise. Multiplied by eta, which is the step size, or the learning rate, times k, which is the number of iterations. Okay, so this is what we have now, and has all the problems that we discussed before. The question is, what can we show? Can we come up with something which is tighter than this? So to quantify the dynamics of Renyi differential privacy in noisy GD, we try to analyze the stochastic processes that model this algorithm. So noisy GD is a discrete time stochastic process. And again, imagine in these two parallel worlds where we have two neighboring data sets, D and D prime. And we have this sequence of random variables that represents the distribution of model parameters at different iterations. Assume that these two processes start with the same distribution. What we are interested in is that what is the divergence between these two parallel distributions as they advance through the training. So we want to quantify the Renyi divergence between theta k and theta prime k and compute a bound on that, right? But first, what we want to know is how this R, the Renyi divergence changes, and what it depends on. And when we talk about the dynamics, we want to know what is the rate of this over time and space, in our case, with respect to alpha. So what we do is that to quantify the dynamics of DP, we trace these discrete time stochastic processes with continuous time stochastic processes, which they match the probability distribution of the noise EGD at the time of updates, right? So at any time that we are updating, the two processes, the continuous time and the discrete time processes would have the same probability distribution. So now we have one continuous time process for running the algorithm on D and the other one on D prime. And we can prove that the dynamical system for differential privacy follows this equation, where we have the partial derivative of R here is the rate, the Renyi divergence at time t and order alpha. So here we can compute an upper bound for the rate of privacy loss, which is how much privacy loss changes if we change it by a small amount in t, right? If you move in time a little bit. So this is upper bounded by a constant minus a positive term. And the positive term has the privacy loss and also the partial derivative of the privacy loss with respect to alpha. So something which is very important here is that we know that as we go over different multiple iterations, as we advance in the training process, we are leaking more information about the data. So the privacy loss should keep increasing, right? But what is very important to see here, and this inequality would show us, is that as the privacy loss value increases over time, as we advance over time, then the right-hand side gets smaller. The right-hand side of this inequality gets smaller. Therefore, the rate of privacy loss decreases. So there is less space for the rate. Therefore, the added privacy loss of each iteration decreases over time. And this is what it leads to, that the noisy GD algorithm, according to this analysis what we did, converges exponentially over time to this constant that we have, which is alpha, the order for Renyi DP. S is the sensitivity of the total gradient. We assume here that the loss function is beta smooth and is also lambda strongly convex. So sigma square is the variance of the noise and n is the size of the data set. Eta again is the step size or the learning rate. So as you see, as k increases, then we have a bound, a constant bound on epsilon, which is independent of t or k. The assumption is that we start the process by initializing the model parameters by sampling from a normal distribution, and also the update size should have a bound. This is a very strong result. To just show you how it looks in the plots that we showed before, this is how it looks. So compared to, remember, the previous bounds based on composition, that they were linearly increasing. Here, the privacy loss converges at the exponential rate to its final bound. This is significantly tighter than the previous bounds, which are based on composition. And it shows that if we hide the intermediate steps of the computation, and we allow the probability distributions over the model parameters to evolve over time, then we might be able to compute a much tighter bound for differential privacy on machine learning algorithms. So this is great, but we were curious to know how tight this bound is. So to just finish this presentation, I want to go over this analysis about the tightness of the bound on RDP. We are asking the question of what would be the lower bound. And we can prove that there exists two neighboring data sets and particular star distribution and a particular loss function, for which we can construct a setting where the any divergence between the model's parameters over time is lower bounded by this factor, which has the same convergence rate, very similar to the previous to the true bound. So just put them in one plot. We see that so the straight the continuous lines are the differential privacy bound, RDP bounds, and the dashed lines are the lower bounds, which is kind of a worst case setting that we have managed to construct. And we see that they are very close to each other. So, and for smaller values of alpha, they become indistinguishable. So this means that the bound that we have computed for these families of algorithms could not be further improved that significantly. So I would like to end this talk basically with this plot, that this is a very interesting kind of analysis that we got inspired by the work done on privacy amplification by iteration. That hiding the states of the algorithm should enable you to come up with a tighter bound. But the analysis is completely different. So this is great, and I'd be very happy to follow up with you and discuss these results. The paper is still not out there, but will be available on arXiv in the next couple of days. You can check back on my website for the for the release version of the paper. Thanks again, and I hope that you enjoy the workshop.